Hello, welcome back. We are on chapter 20 now in materials kinetics, which is on the topic of master equations. We're going to see how to use everything that we've learned up to this point about energy landscapes and broken ergodicity in order to calculate the kinetics of any arbitrary system on any arbitrary time scale. So I'm going to walk you through this step by step and how we construct the master equations for doing this, and how we go about solving those master equations on the relevant time scale for the problem of interest. So the outline is we're going to start with transition state theory. Then we go to master equations. And then most of the lecture is spent on how we solve the master equations. We're going to go through this in a stepwise process, where first we're going to include degenerate microstates. Then we're going to use a metabasin approach to solve the master equations for systems that have timescales that cover orders of magnitude differences and having very fast processes and slow processes. And then I will show you how to access any arbitrary timescale, including long experimental timescales or even longer. So transition state theory, or TST, was introduced by Wigner back in 1932 as a way to calculate the rates of chemical reactions. For example, what is the rate of rearrangement of some molecule I into a different molecule J? And that rearrangement involves overcoming some sort of a potential energy barrier. We can visualize this with this double well potential, where you can see potential energy on the y-axis and then some reaction coordinate here on the x-axis, where there is your initial state I, the final state J, and then there is a reaction rate Kij. This is the rate of going from state I to state J. And transition state theory adopts this functional form that we have already seen from our work in chapter 7, that there is some attempt frequency for overcoming the barrier. That attempt frequency is given by nu and is the prefactor here. And each one of those vibrations is like an attempt to overcome this barrier that has a height of delta Uij. The probability of being successful in overcoming that barrier is given by the Boltzmann probability function. So e to the minus delta Uij over kt. This is e to the minus activation barrier that needs to be overcome, delta Uij, divided by the amount of thermal energy that the system has, kt. And if you put this together, then this gives you the rate of transitioning from I to J, overcoming this barrier delta U at a temperature T. Now with master equations, we are going to use these rates from transition state theory here to calculate the evolution of probabilities of occupying different microstates of the system. So the evolution of concentrations or populations or probabilities can be described using a set of differential equations known as master equations. The master equations have the functional form shown here. On the left-hand side, we have the time rate of change of the probability of being in some particular state I. That probability is pi, and this is the time derivative of pi. Then this time rate of change of pi is equal to then a summation on the right-hand side, where the summation is over all other states j not equal to I. And then there are two terms within the summation. There is all of the flow into the state I from J minus all of the flow out of state I to any of the other states J. So the first term here is just the rate from J to I times the probability of having started in J. So if you're in any of the other microstates J, what's the probability of starting there? Times what is the rate of having started there going to microstate I. So that's Kij times Pj. This has a plus sign in front of it because this is the probability of going into I. And then the minus term here is the probability of leaving. So the indices are switched here on the K. So now this Kij is starting in I and going to J, We always start with the first index and go to the second index, times the probability then of starting in I. So what's the probability of starting in I and then leaving I, going to some other state J? And the difference between these two gives you the combined rate of either going into or out of this particular state I. Of course, all the probabilities must satisfy the normalization condition here, where if you sum up any of the probabilities over time, so sum up over all the possible states at any given point in time t, the summation of probabilities must equal 1 to satisfy that normalization condition. Now, remember from our energy landscape lecture that we introduced this concept of a disconnectivity graph as a way to represent a complex potential energy landscape. So for example here, this shows a continuous potential energy landscape on the left, which is the potential energy as a function of bond angle for this 3-atom molecular cluster. There are 3 minima here, these 3 inherent structures, A, C, E, and on the disconnectivity graph, those are represented by these endpoints here, A, C, E, where the vertical placement here is indicative of the potential energy of those 3 inherent structures, but the placement on the X scale is just arbitrary because it's meant to represent some arbitrary configuration coordinate. Then we have 2 transition states here, B and D. B governs the transition between A and C, and that's given here in the disconnectivity graph representation, where if you were to transition between A and C, you have to go through the state B. If you were to transition into or out of state E, that requires going through transition state D, which is shown here. So this disconnectivity graph representation is a convenient way to represent the topology of these energy landscapes. And depending upon how much energy that you have in the system, that tells you whether you are allowed to make certain transitions or if you are unlikely to be able to make some of those transitions. Recall also that if we were to add additional atoms to the system, the energy landscapes become a lot more complicated with a lot more inherent structures. So this disconnectivity graph representation is actually a really convenient way of representing the energy landscape of a system. Now, getting back to master equations, let's start with a simplified energy landscape that has 5 microstates in it, which are arranged following the disconnectivity graph shown here on the right. So the 5 microstates are labeled as 1, 2, 3, 4, 5. 3 of these microstates are degenerate, and that set of degenerate microstates of 1, 2, and 3 is labeled as capital A. The other 2 that are degenerate are labeled as 4 and 5, and those are labeled with a capital B. Now, what it means to say that they're degenerate is that they're effectively the same. They're the same types of structures with the same energy. So 1, 2, and 3 here all have the same energy, and 4 and 5 have the same energy as each other. And so the first thing that we're going to do to simplify the master equations is to incorporate these degeneracy factors into the master equations to reduce the number of master equations that we need to solve. So if you have these 5 microstates in the system, if we were to write out the full set of master equations, that would be 5 master equations for the 5 microstates, 1 for each microstate. So each one has the change of the probability of that microstate with respect to time. So for example, dp1 dt, this is the time rate of change of the probability of occupying the first microstate, then the second, the third, the fourth, the fifth, and so on. And then you've got all of the terms here that are positive are all the flow from all the other microstates into that given microstate. And then the minus terms represent the flow out of that microstate into the other microstates. So 5 master equations, these are all coupled differential equations. So if we can reduce the number of master equations, then we've reduced the number of coupled differential equations, which makes the problem easier to solve. And the first thing we're going to do to simplify that is to incorporate these degeneracy factors. So what we're going to do is note that because all of these microstates 1, 2, and 3 have the same energies, they also have the same probabilities. So P1 equals P2 equals P3, and P4 equals P5 because they have the same energies. And this is not just at initial time, this is at any time because of the degeneracy of the transition rates. Where if you look here, the rate of going from 1 to 2, so going from state 1 to state 2, is the same as going from 2 to 1. And it's also the same as going from 1 to 3, 3 to 1, 2 to 3, 3 to 2. They all have exactly the same barrier. They all occur at exactly the same rate. So there's this set of degenerate transition rates. Likewise, going from 1 to 4 is the same as going from 2 to 4, or 3 to 4, or 1 to 5, 2 to 5, 3 to 5, again, because of the degeneracy here that is built into this energy landscape, and so on. And with the equivalence of all of these transition rates and the equivalence of the probabilities, we know that for any point in time, we have these conditions satisfied, that P1 equals P2 equals P3 for any time, and P4 equals P5 for any point in time. And therefore, we can use this kind of built-in symmetry into this problem here to introduce a set of different probabilities that just represent the collective probability of the set of degenerate microstates. So for example, PA, this capital PA here, is equal to the probability of being, collectively in this set of degenerate microstates. So PA is equal to P1 plus P2 plus P3, which, because P1 equals P2 equals P3, is just the degeneracy there, the number of microstates, GA, which is 3 in this case, times P1. So PA equals GA times P1. Likewise for PB, this is just P4 plus P5. That's equal to the degeneracy of that set, GB, which for this energy landscape is equal to 2, because there are 2 microstates, times any one of the probabilities there, P4. And with this, then we can also simplify our master equations, given that since PA is equal to P1 plus P2 plus P3, that means the time derivative of PA is equal to the time derivative of the right-hand side of that equation, which is just the summation of the time derivatives of the individual microstate probabilities. So dP1 dt plus dP2 dt plus dP3 dt. And similarly for the B set. And if we substitute all of this back into the original master equations, what we get is this upper equation here for the dPA dt. So this has the summation of these probabilities, P1 plus P2 plus P3, and we can incorporate these degeneracy factors in here based on the number of times that each of those terms appears. So now we have a reduced set of these 2 master equations instead of the original set of 5. And then building or using those degeneracy factors, we can write this in simplified form as shown here, where the dPA dt is just equal to the degeneracy of A times the rate of going into A times the probability of being in that other set of degenerate basins B, so PB. So this is the rate going in minus the rate going out. And this is a much simpler form for those master equations accounting for that degeneracy. We can also define effective transition rates that build the degeneracy of the final state into the transition rate. So this K tilde AB would be equal to the degeneracy of the final set there, GB, times any of the individual rates of getting there. Say K14 goes into the set of degenerate basins here, B, and it can do that GB number of ways. And therefore, the effective transition rate here, K tilde AB, is just that degeneracy factor GB times K14. And if we build that in, then that simplifies the master equations even further. And you've got this nice compact form of just 2 coupled differential equations instead of the total of 5 differential equations. And what we know then is if you solve for these probabilities here, that you can distribute those probabilities equally amongst all of the microstates within that set of degenerate basins because of them being degenerate. Since they're degenerate, they all have the same probabilities. So any of the individual microstate probabilities are just equal to that total probability divided by the degeneracy because it's distributed equally across them. So the generalized form then of the master equations accounting for degeneracy is just this time rate of change of dPA dt, and then equal to the summation of B not equal to A. And you've got the flow from all of the other sets of degenerate microstates into A minus the flow out of A using this effective rate that is shown here. So that simplifies the process. But now we get to the more complicated problem of how do we deal with the vastly different timescales that are involved with the kinetics of some system. Now, recall from the last lecture on broken ergodicity, when Palmer introduced the concept of broken ergodicity, he considered three very different timescales. There was the fast timescale, at which the kinetics within a component occur. So this corresponds to these small barriers. So there's very fast transitions within a component. Then there's the medium time scale at which you observe the system. And then there is the much longer time scale that defines the inter-component transitions. And Palmer assumed that those inter-component transitions were not allowed. So he assumed that we had confinement of the system. What we're going to do with this master equation approach is to get rid of that assumption of confinement. And instead of these sets of microstates being denoted as components, we're going to call them metabasins. So if we have a potential energy landscape here, it has any number of basins, and we're going to group those basins into metabasins where each of the metabasins satisfied the condition of internal ergodicity, but we're not going to assume confinement. Instead, what we're going to do is solve for the kinetics of the system using a reduced set of master equations that describe the inter-metabasin transitions. In other words, we're only going to use the master equations on the time scale that corresponds to the inter-metabasin transitions, because everything that's happening on a much faster time scale can just be distributed according to equilibrium statistical mechanics within its own metabasin. So we're going to have a probability of being in metabasin alpha that's going to evolve based on its reduced set of master equations. But for whatever the probability of being in metabasin alpha is, that probability gets distributed among all of the basins within the metabasin following equilibrium statistical mechanics over the restricted ensemble of the metabasin itself. So this builds upon Palmer's approach, but relaxes the assumption of confinement and then provides a mathematical framework for actually solving the problem. So we're going to now consider another sample energy landscape shown on the right here, where now we've got these two sets of degenerate microstates here, A and B, and these are, let's suppose, grouped into a metabasin alpha, and then we've got another set here, C, D, and E, which are grouped into a metabasin beta. So we're using numbers to represent the microstates, capital letters to represent the sets of degenerate microstates, and then Greek letters to represent the metabasins. Now, the probability of being in a given metabasin alpha, we're denoting here as F alpha. F alpha is just the summation of occupying any of these sets of degenerate microstates here with the capital Roman letters PA. So this is summing up over all the A within alpha. And within that A, you can sum up all the individual microstates with the little I. So this is just adding up all the microstate probabilities within a metabasin gives you the total metabasin probability here, F alpha. And if we add up over all the probabilities of all the metabasins, that summation equals 1 because every microstate has to be inside one and only one metabasin. So summing up over all those probabilities gives you a total probability equal to 1. Now, what we need to do is to define our restricted partition function of the metabasin, so Q alpha. And Q alpha is just summing up over all the sets of degenerate basins within alpha. The degeneracy is GA, so that's the prefactor out in front. It's how many degenerate basins that we have. And then E, the Boltzmann factor is E to the minus, then the internal energy that's associated with that set of degenerate microstates over KT. And we sum this up over all the different sets of degenerate microstates within the metabasin. And that gives us the partition function that corresponds just to that metabasin. So all we're doing here is summing up over all the probability factors within the metabasin. That gives us the metabasin partition function. And then using the metabasin partition function, we can get the thermodynamic properties of the system. But more importantly here for this problem, within the metabasin, the microstate probabilities, in other words, the individual basin probabilities, follow equilibrium statistical mechanics within that restricted ensemble. So the PI within alpha, this is the probability of being in some basin I within the metabasin alpha, is just equal to the F alpha here, the probability of being in that particular metabasin, then divided by the partition function of that metabasin alpha times the Boltzmann probability factor of that particular microstate. So all this is doing is taking the total probability of being in the metabasin, F alpha, and distributing it to all the microstates within that metabasin following equilibrium statistical mechanics, following this Boltzmann distribution. And that is the beauty of this approach of accounting for broken ergodicity, is that when you have internal ergodicity within the metabasin, you don't need to calculate the kinetics within that metabasin on that really fast time scale, because the kinetics are so fast that you've achieved internal ergodicity, which means you've achieved a local equilibrium within the metabasin itself. So you can just distribute the probabilities within the metabasin following equilibrium statistical mechanics within that restricted ensemble. Now, if we want the thermodynamic properties within the metabasin, you can rewrite here the PA is equal to the F alpha over Q alpha e to the minus free energy of A over KT, where this free energy factor is accounting for this degeneracy factor here, GA. So basically we can take this degeneracy, pull it into the argument of the exponential, and that gets multiplied by a minus KT, and then the K log GA here is the entropy part. So this is the Boltzmann entropy of that set of degenerate basins, SA equals K natural log of A, using then the definition of the free energy. In this case, this is the Helmholtz free energy, which is the internal energy minus temperature times the entropy. That gives us the free energy of the metabasin. So another way of writing these probabilities is, instead of writing it in terms of a degeneracy and an internal energy, you can write it in terms of a free energy. Now, how do we write the reduced set of master equations for the metabasins? We're going to follow a very similar approach that we did for the sets of degenerate microstates. We're going to start off with the full set of, in this case, 5 master equations here for PA, B, C, D, and E. We're going to note that the metabasin occupation probabilities here, F alpha and F beta, are just the summation of the probabilities of all the microstates within those metabasins. We're going to use that and the equivalence of many of the transition rates in between to write simplified master equations here. These are the master equations for each of the 2 metabasins now, dF alpha dt and dF beta dt, where we've got the summations of all of the sets of degenerate microstates within each metabasin. And then we're using this simplified notation that we introduced last time, that K tilde incorporates the degeneracy factor into the transition rates itself. Now we're going to note that with all these various transition rates, how many of them are actually unique? For this case, only 5 of them are unique because the rate of going from C to A is the same as the rate of going from C to B. Likewise, going from D to A is the same as going from D to B, and so on. Because of how the landscape is constructed, not all of these transition rates are unique, and we can take advantage of the fact that not all of them are unique to simplify this problem. So simplifying these terms reduces the number of variables and also shows that we can group these terms together where you've got summations of the individual degeneracies here, like GA plus GB occurs in several of these terms. So this is the total degeneracy within metabasin alpha. Likewise, GC plus GD plus GE occurs several times. That's the total degeneracy within metabasin beta. So we can then define the total number of microstates within a metabasin, and now we're using N sub alpha for the metabasin degeneracy, or not really degeneracy, but total number of microstates within the metabasin, because within the metabasin, they may have slightly different energies. As you can see, A has a different energy than B, C, D, and E all have different energies as well. But that total number of microstates within metabasin alpha is just the summation of all of the degeneracies for all the sets of degenerate microstates within the metabasin. So with that definition, then this simplifies how we can write these master equations, because now we can use N alpha and N beta. Likewise, we can define effective intermetabasin transition rates to simplify this further, where the effective intermetabasin transition rate W from alpha to beta is then equal to N beta, the total number of microstates in the final metabasin, divided by F alpha, the probability of having started in the initial metabasin alpha, times then this weighted probability factors here for the transition rates going from either A to C or from B to C. So you're starting at slightly different energies here with A and B, even though they have to overcome the same or go through the same transition state to get to the other metabase. And the activation barrier is actually slightly different because of A starting with a higher energy compared to B. And so this is giving you the effective average rate, accounting for those differences between KAC and KBC, because you've got the probability of starting in A times its rate of leaving, and then plus the probability of starting in B times its rate of leaving. So this then gives us effective intermetabasin transition rates, and we can use those intermetabasin transition rates then to simplify the number of master equations here down to just the same as the number of metabasins that we have defined. So in this case, we've defined 2 metabasins. There's one master equation for each of the metabasins. So there's one that governs the kinetics of metabasin alpha, and then the other that governs the kinetics of metabasin beta. And strictly speaking, you don't even need the 2 because the total probabilities add up to 1. So all you need is, if you've got n number of metabasins, you only need n minus 1 master equations, because the last one is just 1 minus the summation of the probabilities from all the other ones. But I'm writing it out explicitly here just for clarity. And the cool thing about this is we are now solving for the kinetics of the system on the time scale of the intermetabasin transitions. So we've defined a time scale that is relevant for the problem, and that definition of a time scale tells us what things are fast and what things are slow. So everything that's really fast gets grouped together within a metabasin, and we don't have to solve for the kinetics on that fast time scale because it's just distributed according to equilibrium statistical mechanics. Everything that's slow then defines the intermetabasin transitions, and the way that we have partitioned the landscape into these metabasins is governed by what we choose as that relevant time scale. And so this, focuses our calculation time on the relevant time scale of the experiment defined by that observation time scale. So our generalized form for the master equations governing inter-metabasin transitions is shown here. This is the df alpha dt, and we've got the summation of all the rates going from all the other metabasins into our metabasin, and then minus all of the rates leaving our current metabasin going to the other ones using our effective average inter-metabasin transition rates. And we haven't really made any assumptions here. This is all fully rigorous. The next step becomes, how do we figure out how to partition the energy landscape into metabasins? And this becomes one of the most important problems in implementing this approach, because the partitioning process depends on the topography of the energy landscape and also the topology of the energy landscape. It depends on the temperature of the system, and it depends on the observation time, which can either be defined directly or related to how fast the temperature of the system is changing. Or if you've got much faster changes of temperature, that corresponds to a much shorter observation time. So how do we account for this? Let's consider an example energy landscape shown here. This is a 7-basin energy landscape where each of the 7 basins are labeled 1 through 7. The continuous energy landscape is shown on the left, and the disconnectivity graph representation is shown on the right. Now, I think it's pretty clear that we got a distribution of rates here, a distribution of transition rates between different pairs of basins. And if we use transition state theory, we can define the transition rates between any pair of basins. So this would be a transition rate matrix here, K, that has all of the rates from every one of the basins to each of the other basins. So the transition rate from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and so on. Using transition state theory, then that transition rate is just given by the frequency, nu ij, times the Boltzmann factor e to the minus delta u ij over kt. So each one of those individual rates is given by transition state theory. When we account for degeneracy factors, that can build the degeneracy factor here, gj, into the transition rate, as we have already shown. This is the degeneracy of the final state, because that tells you how many ways that you can get there. And this gj can get pulled into the argument of the exponential. When it does that, you pick up a logarithm here. Why would we do that? It's because this degeneracy factor can vary by orders of magnitude. And so computationally, it often makes a lot more sense to deal with the logarithm of degeneracy factors instead of the degeneracy factors themselves, because it's easier to represent that numerically in the computer as a logarithmic value, because g varies by so many orders of magnitude. But getting back to this landscape here, you can see that we can rank all of these energy barriers. All of these energy barriers exist in the problem. The delta U going from 5 to 1, from 5 to 2, from 4 to 2, 1 to 5, and so on. And there is the highest energy barrier here, which is the highest one on this activation barrier plot. And then you've got the smallest barriers here, which are within the set of degenerate basins here between or among 1, 2, and 3. So increasing on this axis is a higher activation energy. A higher activation energy means slower kinetics, so the faster transition rates are actually lower down on this graph. And we can make a similar ranking of transition rates, where you've got really fast transition rates at the top. These would be the fastest transition rates at the top, and then the slowest transition rates at the bottom. And this is helpful because we're going to define some relevant time scale on which we're solving for the kinetics of the system. That relevant time scale is going to be the divider for what constitutes fast versus slow. So if we have some sort of threshold here, a threshold transition rate, everything that is faster than that, everything that's a higher transition rate, is considered to be fast, and we'll consider to be equilibrated on that relevant time scale. Everything that is slower than that is considered to be slow. And this threshold is chosen such that it guarantees internal ergodicity. In other words, it guarantees that any collective set of microstates that are connected by fast transitions are able to achieve internal ergodicity, which means that they're able to equilibrate locally among that set of microstates. For example, a threshold here, this is just a typical threshold, might be how fast are you changing the temperature? So the absolute value of the time rate of change of temperature divided by or multiplied by 10 inverse Kelvin. And this would give you a kind of threshold that you could use in a computer program to do this that is reasonable for ensuring that internal ergodicity is a valid condition. But how do we do this partitioning? So we've got this ranking of different transition rates here, and we've got our sliding threshold here. If we are at very high temperatures, the entire landscape is a single metabasin, because at high temperatures, all of the microstates are accessible. All of the transitions are fast at high temperatures. That means the entire system is one metabasin, which means that we don't even need master equations because the system follows equilibrium statistical mechanics. Now, as we cool the system down from high temperature to low temperature, as we cool the system down, this sliding threshold is coming upward. And the first set of transitions that become slow are going to be the ones that correspond to the highest activation barrier. And that's going to correspond to the first partitioning of the landscape into metabasins. That first partitioning of the landscape is like taking this disconnectivity graph, and you see the little scissors icon here. It's like cutting it at wherever that highest activation barrier occurs. So it's taking this single metabasin landscape, cutting it where the highest barrier occurs, and it's cutting it into these two smaller disconnectivity graphs now, where each one of these smaller disconnectivity graphs denotes a metabasin. So if we cut it at this highest barrier here, this gives us a set of basins 1, 2, and 3, which are within metabasin alpha, and then the other set 4, 5, 6, 7, which are within metabasin beta. What this means is that the transitions within metabasin alpha are all fast. They all satisfy internal ergodicity. The transitions within metabasin beta are also all fast. This also satisfies internal ergodicity, but the kinetics between the metabasins are becoming slow. And so we can no longer assume internal ergodicity there. So we need to solve for the kinetics of the system then between or using master equations just between these two metabasins. How do we actually do this partitioning? What we can do is to take our transition rate matrix here, the matrix that we set up, this K matrix of all the transition rates, and you look at these slowest transition rates here and see where is it that we're ending up with these transitions. These all have as their second index 1, 2, 3, 1, 2, and 3. So these all involve getting to 1, 2, or 3. What we do is we take our whole matrix here and we cross out the rows 1, 2, and 3. So the rows that correspond to that second index or that destination index, and we cross out the columns for the same indices here, 1, 2, or 3. Everything that gets doubly crossed out here, in other words, the 1, 2, and 3, that forms one of the metabasins. So the microstates 1, 2, and 3 here correspond to this then reduced transition matrix here with just 1, 2, and 3. Everything that's not crossed out at all is the other set. So that's 4, 5, 6, 7. That is the other metabasin. So the set of microstates 1, 2, and 3 that are doubly crossed out gives you one metabasin. The set of microstates that are not crossed out gives you the other metabasin. And the transitions between the two are governed by master equation kinetics. Now, as you continue to cool the system, that sliding threshold continues to go up. The next largest barrier, the next breakdown of ergodicity occurs with this next highest barrier here, which is within metabasin beta. So this is going to take metabasin beta partition it into two metabasins, where now there's this new metabasin beta, which is just 4, 5, and then a metabasin gamma here, which is 6, 7. So we started off with just one metabasin. The first partitioning gave us two metabasins. The second partitioning now gives us three metabasins. Again, here, this is with a destination of 6 and 7. And so you cross out the rows, cross off the columns. One of them is going to be doubly crossed out. That gives you one of the metabasins here, 6 and 7. The other one is not going to be crossed out. That gives you the other metabasin here, beta. So now we've got three metabasins, and we've got three master equations that govern the kinetics among metabasins alpha, beta, and gamma. And what we can see is if we plot the number of metabasins as a function of temperature, at high temperatures, there's only one metabasin because at high temperatures, the system is ergodic. There's internal ergodicity across the entire system. There's plenty of thermal energy to overcome the barriers and equilibrate. So we just follow equilibrium statistical mechanics at high temperatures. We don't even need the master equations because everything is in a single metabasin. As we cool the system down, there's a first breakdown of ergodicity where that one metabasin transitions or partitions into two metabasins. This is the first breakdown of ergodicity. If you continue to cool, there's a second breakdown of ergodicity that now gives us three metabasins. If you continue to cool again, another breakdown of ergodicity where now we have four metabasins, and then again where we have five, and then eventually we get to a low enough temperature where all of the transitions are slow. When that happens, then every individual basin is its own metabasin. So here in green, at high temperatures, the system is at equilibrium because all the microstates are in a single metabasin. In yellow, it's the first breakdown of ergodicity, the first partitioning of the system into metabasins. And then at very low temperatures, each microstate, each basin is its own metabasin. So this gives you the different degrees of fully ergodic system at the high temperature limit, fully non-ergodic system at the low temperature limit, and then these various steps of the loss of ergodicity as the system is cooled. And if we use our master equation approach as outlined here, solving it for the metabasins, you can see that the black line, there's another line that's right underneath it, that you've got perfect agreement here between either solving for the full set of 7 master equations for each one of the individual microstates. It gives you exactly the same results as if you did this metabasin partitioning, distributing the probabilities of the metabasins within the metabasin following equilibrium statistical mechanics within each metabasin. They give exactly the same results. So it works well. And the beautiful thing about this is that this enables you to access any time scale. This shows you an example. This is a volume temperature diagram where we've covered here 25 orders of magnitude of cooling rate. This would be unthinkable with molecular dynamics simulations. It's also unthinkable from experiments because you simply can't access that wide range of cooling rates. But with a master equation approach, you can do that. Because the relevant timescale is the relevant timescale for that given cooling rate. So for the faster cooling rate, what's defining the relevant timescale is a much shorter time compared to the very slow cooling rate, which occurs in a much longer timescale. And you can see how this breakdown of ergodicity starts off at high temperatures for the fast cooling rate because you're giving the system less time. And then as you lower the cooling rate, you're giving the system more and more time to stay ergodic, and it's shifting this breakdown of ergodicity to lower and lower temperatures. And the computational time for all of these is roughly equivalent with this master equation approach. So it's a really powerful technique. So to summarize, transition state theory governs the kinetics of transitions over energy barriers. These kinetics can be described in terms of a system of master equations. Most real systems have transition rates that span many orders of magnitude, and so it becomes really helpful to leverage everything we learned about broken ergodicity to focus our calculation time on the time scale that matters, where anything that's much faster than that follows internal ergodicity and then can use equilibrium stat mech in between. Then we focus our calculation time on solving the kinetics of that reduced set of master equations between metabasins at that desired timescale. All right, thank you very much. If you have any questions, let me know. And otherwise, I will see you next time.